Yeah. Uh, yeah. Page exactly is mine.
One thing is that this seems to come down occasionally. So you can see it, you can just
hide floating meeting controls. Yeah. Yeah.
think it's just,
I don't mind electrons.
Okay, that's Sharmila Balamurugan from Warwick.
Thank you. Thank you for the opportunity, and I especially wish to thank Professor Oppenheim and Professor Post for giving me this opportunity. This talk is going to be a little different from what you've been having since morning. This is going to be more on how you're going to sense the gravitational, the space-time fluctuations or effects of quantum gravity or other interpretations of gravity, rather than gravity models themselves. So we're going to talk about how you can detect space-time fluctuations in laser interferometers, and also talk about the specific role correlation plays in that. This work was done in collaboration with Sander from Caltech and Animesh Datta from University of Warwick. This work was recently put up on the archive, and this is a preprint for anybody who wants to check it out. This is a brief overview of the talk where I'll first motivate why I'm talking about space-time fluctuations, first of all, and then talk about how it affects the interferometric output and how we identify specific signatures which correspond to different gravity models or other the statistical properties of correlation functions of space-time fluctuations, and then finally summarize with some results. I'll also kind of highlight some of the work that goes on in my group, but yeah, that's basic advertisement. Anyway, getting back, the space-time fluctuations, as people here are probably well aware of, was basically introduced as vacuum fluctuations of gravitational field. And as you know, bosonic field vacuum is not a complete absence of bosons, but rather random creation and annihilation of bosons. And in the context of electromagnetic field, measurement of the effects of these random fluctuations indeed led to the foundations of quantum electrodynamics. The measurement of lamp shift practically laid the foundation stone for understanding the fundamental nature of electromagnetic field. So in that context, it was considered that detecting space-time fluctuations, which were considered vacuum fluctuations of gravitational field, could possibly mean detecting the quantumness of the field or initially. And this was first proposed by Wheeler as space-time foam, where it was basically random fluctuations at the Planck length scale on a flat Minkowski spacetime. But since then, space-time fluctuations have been practically a leitmotif in different theories of gravity interpretations, which range from completely quantum field theoretic viewpoints of gravity to classical models of gravity, which are emergent from quantum entanglement of holographic degrees of freedom, or even to stochastic gravitational wave background. Space-time fluctuations occur in a wide range of interpretations of gravity and models of gravity. And they have, because they come from different theories of gravity, they also have wide variety of statistical properties which these fluctuations can possess. For example, the correlation length, if you think of effective quantum field theories, it's going to be Planck length scale, whereas if you consider holographic models, it's going to be a long range correlation is going to be possible. So, to some extent, the statistical property of these fluctuations is kind of independent of the origins of the spacetime fluctuation. So, in a way, looking at statistical properties is going to help us look at gravity the different gravity models without going very deeply or being rather agnostic about where these fluctuations are coming from. So, what is the aim of this work? I've talked a lot about space-time fluctuations now. So what are we trying to do? Now, there are experiments which, since 1999, when Amelino Camellia said interferometers could be used for the purpose of detecting, searching and studying space-time fluctuations, there have been several high-precision interferometers that have been developed and being used for this purpose. Now, we want to see if what kind of experimental signature you can see when you have the different gravity models under consideration. There should be signatures that are specific to the various gravity models, and building a catalog of such signatures will be helpful. Now, what are the things that can play a role in this catalog? What are the different parameters that we have to modify? One parameter can be from the experimental side, which is the geometry of the Michelson laser interferometers that we're talking about. I'm making it specific, saying it's Michelson laser interferometer, because there are many kinds of interferometers that can be used, starting from interferometers that involve atom interferometry and even other kinds. So let us be specific. This work is going to be on Michelson laser interferometers, and one of the parameters that we can think of varying is the geometry of Michelson laser interferometers. This is interesting because what is available currently in the form of proposed and planned and existing interferometers are a certain set of geometries, which we'll consider. There are also other kinds of very creative geometries which involve 3D interferometers with bent arms going crisscrossing each other and all that, which are under consideration. For example, in Cardiff, they are trying to build such a 3D interferometer, but we are not going to consider those. It's going to be more standard, what is currently possible, which is already existing. As far as the gravity models are concerned, I already told you about how correlations were playing how there were very widely varying statistical properties for the correlation functions, and classifying by the property of correlation for the different space-time fluctuations is much more effective rather than considering the origins of these fluctuations. So we are trying to classify by correlation. So we have kind of set up 3 correlation classes and 2 types of setup geometries. And we want to build a kind of a table of, or a catalog of experimental output. So this is the basic agenda of what we are trying to do. And why we are trying to do it? Because experimenters really appreciate this effort, because they are able to now at least have an idea of what to expect. And also theory people, on the theoretical side, it is useful because you can kind of try and get a bound on what should be the different parameters, or at least you can help the experimenters bounding the different free parameters in each of the gravity models. Now, for the 2 types of setup geometries, the one we can first consider is the Michelson laser interferometer, or MLI, from now on, without arm cavities. What do I mean by that? Now, there's a schematic diagram of 2 interferometers that are parallel, co-located and co-aligned to each other, which means both the arms are parallel to each other and they are separated by a small distance. This I've done so because most of the interferometers that come under this category, which is Quest and GQuest, currently operational and one is planned. GQuest is planned, Quest is currently operational. These are basically two interferometers that are set up this way so that they can get the least amount of errors by looking at the cross-spectral density from the outputs of the two interferometers. So let us consider one interferometer, which is the solid one, for clarity. There you can see that it doesn't have arm cavities, by which I mean light entering the two arms after interference at the beam splitter goes just one round trip in each arm and comes back for an interference. Actually, the beam that gets split at the beam splitter goes just one round trip in each of the arms and gets interfered, experiences interference at the beam splitter to be measured at the output port B. So there's only one round trip in this arm. So there is, in contrast to the setup on the right, which is MLI with arm cavities, which is, can I hide this? Yeah. So this is a setup which is more familiar, perhaps because it is the setup of LIGO, where the light that enters at this point in the two arms undergoes multiple round trips within each arm before it interferes again at the beam splitter to be measured at the output port B. So these are the two geometries that are currently in, Quest is operational and so is LIGO. GQuest is being set up. So yeah, relevant geometries that we are considering. Also for notational sake, we are in the talk, I will talk, when I mention E out, I'm talking about the electric field of the output light, which is detected at the ports B1, B2, or B, as the case may be.
So why don't they operate this one in the same way as beam cavities? Is that difficult?
No, this is because there are some theories that propose that if you have arm cavities, they won't be able to see the signal of those gravity. Yeah, they'll average out. But yeah, so they have both these geometries to figure out what can be done. This is just because it's going to be completely a theoretical talk. I just wanted to introduce an experimental element. This is the setup of the Quest, which is there at Cardiff. You can see that there are two interferometers, rather the two places where the beam splitter should go in. It's a vacuum chamber. They'll pull out the air from there. So you have two chambers and the beam splitter would be placed there. The two arms of the interferometer are visible. It's a 3-meter long setup, so it fits within a laboratory space. And yeah, this was during when it was built. This was taken about 2 years ago. So now it's operational, and this is all in a clean room now. You can't even enter without wearing a full jumpsuit. So what are we doing with this? We are modeling metric fluctuations and its effects by first considering a spacetime metric of this form, where there's a Minkowski flat spacetime metric on which we add a fluctuation W only to the G00 element. This is because we are working in the non-relativistic limit and we can afford this, just like how Caroli-Hazy did before us and so many others. So the assumptions about W include that W is much, much smaller than 1, and it's a stationary process with the autocorrelation function having a gamma S, which denotes the fluctuation strength, and rho, which we'll call the correlation function, which will have LR in it, which is the correlation length, which parameterizes the correlation length. This is applied to the relativistic wave equation. Just for clarity, this is the relativistic wave equation in which we apply. And it is the F that we want to solve for. We actually want only the jth component of E. So we are interested in obtaining minus C F0J from this expression, which involves the Riemann tensor and the curvature, Ricci curvature tensor, Ricci scale, Ricci curvature, and all of this. And yeah, it requires a lot of assumptions, which I'll list later on. But once you solve for the electric field, you can substitute that into the spectral density formula shown here, which involves the fourth moment of the electric output electric field output. And you take a cosine transform of the fourth moment, then you can obtain the spectral density. And even this formula, if you make I equal to J, that gives the power spectral density, which is the thing of relevance for us in the interferometric setups. Then here, I'm denoting everything in terms of a frequency parameter nu, which has been made dimensionless using an inverse time, which is the round trip time. So we are calling it FLRT, which is the inverse round trip time. And nu has been made dimensionless with respect to that. So I showed you the relativistic wave equation. We cannot solve for it without implementing some of, without assuming a few things. So the assumptions involved are biconal approximation and slowly varying envelope approximation, by which we assume that the space-time fluctuations that we are considering are having a correlation length which is at a scale larger than the wavelength. And also the time range in which the fluctuations happen is larger than 1 over frequency. So the length scale lambda and the 1 over frequency sets the smallest length scale and the smallest time scales in the problem. Stationarity of the metric fluctuation is assumed, which I already mentioned. And we also assume that the correlation function is isotropic in space. The fourth assumption is not critical. We can let go of that if there is a need, but the expressions came out very smoothly and it was analytically very easily handleable. And for the models that we were considering, it was not a problem. So we used that.
So,
Yeah.
so you do not measure very small fluctuations here.
That is actually partly our constraint for simplifying the equations, but also because in an interferometer, they are assuming that already. So.
And why you have only the time-lag component fluctuating?
That is because we are in the non-relativistic regime and we can do this. It is equivalent. We have actually in our paper, we have showed that even if you assume a more general fluctuation, you would be able to get back to the same kind of expressions that we have. Yeah.
But this seems like you need the wavelengths to be Planck scale.
No.
That's the correlation length is of the space-time fluctuation.
Yeah, what we are saying is that you cannot look at things that are smaller than the wavelength, which is about a micrometer here. So an actual Planck's length scale fluctuation cannot really be captured by interferometer. You might need to either lower the wavelength or look at diffraction effects. Once you consider diffraction effects, it becomes harder because none of the detectors in the interferometer are exactly tuned for capturing diffraction effects because the detector at the end captures the entire beam. It's not actually seeing what's happening in the beam profile. So even if we assumed, we let go of that assumption in the calculation and made our calculation non-tractable, it's not really helping the experimenter because they have no way of looking at the diffraction effects as of now. We have future plans of looking at it because our experimenter suggested that it might be possible, at least in the small scale interferometers, unlike LIGO, where changing the setup is a huge problem. So, yeah, the final one is a check, not exactly an assumption, but I included this because we are also checking to see if The resulting random process in path difference is also stationary. This is a condition that we have to do because we are using Wiener-Khinchin theorem to get the particle density, and that is not valid for non-stationary processes in path difference. So we had to do this check. For anything that violates the stationarity at this level, you cannot exactly use the particle density observable to really look at such noises. So again, requires more work on measurement processes and things like that. So that part of it is ongoing, but for this work, we have assumed, we have checked for stationarity and used results only which are within the regime where the resulting random process is stationary. So what is the approach? What do we do? How do we calculate the spectral densities? I already showed you the formula that we used, which was the correlation integral approach. We also used the response function approach where we got the response functions of the detectors, which is the interferometers in this case, and took the four-dimensional Fourier transform of the two-point correlation function and obtained the path spectral density using the response function approach. The main reason why I'm highlighting this is because the response function approach clearly tells us the difference between an MLI without arm cavity and with arm cavity, where you can see that the interferometric response function carries forward, except that for the MLI with arm cavity, you have an additional response function, which is the Fabry-Perot cavity response. So MLI with arm cavity is actually enhanced by this Fabry-Perot cavity response. We'll come back to this. I'm just highlighting it for now. We'll come back to this later on. So, so far we talked about geometry of the interferometers, how we obtain the path spectral density. We'll now go to the crux of the matter, which probably you're more interested in, which is how we separate the correlation classes for the different gravity models. We use two criteria. We try to keep it as broad as we can, but the first criteria is induced symmetries, which are present in the correlation function, which probably signifies some underlying symmetry in the spacetime fluctuation itself. The induced symmetry that we are considering is class A, where we are considering correlation functions that factorize into a spatial part and a temporal part. The classes B and C are functions that cannot be factorized. And the criteria too for splitting it into further into two classes, the non-factorized part, is decay behavior, where we can either look at inverse decays of the correlation function as you increase the space-time separation, or an exponential decay. You might ask why inverse decay instead of saying polynomial decay. Yes, polynomial decay is something which is more general. We could have said that, but in the gravity models that we looked at, there were many more models that talked about inverse decay than a more general polynomial decay. There were a few models. One is a modification of a Caroli-Hazy model, in fact, where there were decays which are with a higher power, but predominantly we saw more inverse decay models, so we considered this. Correlation class A is the factorized correlation class, where you have the space and time temporal parts factorizing out. An important model that comes under this case is Oppenheim's model. This, I think, is from an earlier paper in 2023, where this factorizes into a spatial part and a temporal part this way. This delta is a delta correlated noise, and hence you get a delta in time. And this is actually a renormalization of something that goes as an inverse decay. So you have this model, which we considered in our work. And you notice here immediately that the correlation length LR parameter gets cancelled out if you want to set the units right for the correlation function. So this effectively becomes a model where you have only one parameter, which is the strength gamma S. And it becomes independent of LR. So when we have to scale the path spectral densities to a dimensionless form, we use we have only gamma S and the interferometer arm length L and C, and we develop this parameter to make it dimensionless. And this is the interferometric output that you get, the power spectral density versus the scaled frequency nu. Nu, if you remember, is the frequency that was made dimensionless with respect to the inverse round trip time. Now, this is independent, the scaled power spectral density is independent of L, the interferometer arm length. That is evident from the formula that we have for the SNC. And you can see that none of it is actually dependent on L. It's an integral which is over U1 and U2, which is both a numerical integral, and nu is dimensionless. So yeah. The trends were obtained numerically here, but you can even see for a general factorized correlation function, we will be able to say how at a long range, at high frequency limits, it should go as 1 over nu squared. It's possible to show it. For the inverse correlation class, which is the class B that we talked about, we considered two subclasses within the inverse correlation class, which is where we considered inverse with respect to the spatial separation, which is just the Euclidean separation. The other is a space-time separation, which is space-time separation of this kind, the ds squared kind of type. So the spatial separation is relevant in many models. One is the Pixelon model, which is given here in the 2023 paper, PRD paper. It is relevant even for the Caroli-Hazy model, and even in effective quantum field theory models, which are proposed. One such example is the Dane-Carney paper in 2024. The space-time separation is just a generalization of this, which we tried. Both of this, if you notice, is an effectively single parameter model because the LR just becomes a product with gamma S. So the product gamma S LR is still a single parameter. And you can scale the PSDs now with the product gamma S LR in it. And this is the scaling factor versus the scaled frequency nu. The interferometric output is shown here. And this is the expression that we obtained. And again, this is just an integral over U1 and U2, which are numerical factors. And the delta parallel and delta perpendicular are also ratios of delta J with interferometer arm length. So again, this is independent of the interferometric arm length. And irrespective of which interferometer you're trying it on, this should be the shape and this should be the exact form that you're getting. Exponential correlation class C is the actual two-parameter model that we are getting because the correlation length falls into the exponential function. And this is relevant in both quantum and semi-classical interpretations of gravity. And the two subclasses are again dependent on whether the exponential decay happens with respect to spatial separation or space-time separation. Sorry, this reference just carried forward from the last slide. The second reference is a mistake. I'm sorry. The first one is the true reference. Yeah. Oh, by the way, I should have explained this part even in the earlier exponential correlation class. The theta function there makes sure that we are considering only the non-local correlation part and not the local correlation, which could be causally correlated. Now to the scaled PSDs. Again, for the exponential correlation class, we use the same scaling as the inverse correlation class because here too there is an LR dependence. And if you see now that the interferometric output has an actual dependence on LR by L. So if you vary this parameter, you get different outputs. And this is not anymore independent of the interferometer arm length or the kind of setup that you're using. This you have to model for every specific setup. But it's still the same expression that has to be just evaluated for every setup, but still this happens. And you can, okay. When you when you make the scaling different, you can also make, in this, you can still see that it kind of has a high frequency behavior where it goes as 1 over nu squared, and there is a dependence on kappa. But if you make the scaling into kappa, it actually becomes even clearer how if you increase kappa, the interferometric output, the PSD also increases. And if you the time at which as frequency at which it starts the high frequency behavior, the decay behavior also gets shifted to further higher and higher frequencies as you decrease kappa. So this I compiled as a catalog for you to see that the interferometric output is distinctly different between the 3 correlation classes and even the subclasses. And one can characterize the different behavior in terms of 3 characteristic signatures: the low frequency behavior, the high frequency behavior, and how it depends or is independent of the interferometer arm length. So these are the 3 characteristic signatures that we have identified. And to observe all 3 signatures, the Michelson laser interferometer should be sensitive in the range at least between nu equal to 0.1 to nu equal to 10, roughly. Quest, if you notice, which is the 3-meter setup, which is there at Cardiff, the sensitive bandwidth is 0.03 nu to 78, which is definitely sufficient for observing all 3 signatures. GQuest, which is a setup which is being planned at Caltech, which is a 5-meter setup. The sensitive bandwidth is 0.42 nu to 2.1, which is narrower, yes, than Quest, but still you can roughly see all 3 signatures. LIGO, on the other hand, which has higher sensitivity than both at lower frequencies, which is interferometer arm length of 4 kilometers, that works in the low frequencies, as I stated. It has a higher sensitivity, but it works completely in the low frequency from about 10 power minus 4 nu to 10 power minus 1 nu. So you're at a range where you cannot observe, or you can observe only the low frequency behavior. So you're slightly at a disadvantage when you come to LIGO. So as far as observing all 3 signatures and distinguishing between the different correlation functions, the tabletop interferometers, Quest and GQuest, do better. Now, coming to MLI with arm cavities, I had already mentioned how the Fabry-Perot response enhances the power spectral density. The Fabry-Perot response, if you compute it for LIGO, which has the transmission coefficient of 0.014 for the mirror, which forms the arm cavity, the Fabry-Perot response amounts to roughly 10 power 5, which means the signal is enhanced by a factor of 10 power 5, which is good. For example, in the inverse correlation function, you're able to see that the blue line, which is the signal which you expect from Quest, the red is the signal that you expect from LIGO. You can clearly see that it is completely above the signal. And the peak at nu equal to pi by 2, which is the light round trip frequency, you can see that the peak is enhanced by the factor 10 power 5. Now, if you get to the exponential correlation function, on the other hand, we already saw how the exponential correlation function had a dependence on kappa, which is LR by L ratio. Now, in LIGO, when you compare it with Quest is a 3-meter setup, LIGO is a 4-kilometer setup. So you have a difference of 10 power 3 in arm length. So kappa would be 10 power minus 3 smaller for LIGO. And there is a suppression which comes from the kappa factor for the LIGO signal, but also a gain which is coming from the Fabry-Perot response. So that's why you see part of the signal is lesser than the signal that you expect from Quest. And the peak, however, exceeds the signal from Quest. So this LIGO still retains its advantage, but if you have a correlation class which goes like, say, kappa squared or something, then you're in trouble. It wouldn't anymore retain the advantage. So as far as the results go, we saw that the laboratory scale setups with like Quest and GQuest have the broad bandwidth that's necessary for distinguishing between the different correlation functions. LIGO, on the other hand, is better suited for detecting the bare presence or absence of correlation functions, irrespective of what the correlation class is, because the peaks that you saw, you're detecting only the peak there. There's no low frequency behavior and high frequency behavior. If you're able to detect the peak, you have some presence of space-time fluctuation. So it's better suited for detection of bare presence or absence. Now, this is a blatant advertisement of what happens in my group. We also look at other probes, which is there are other PhD students who work on how space-time fluctuations affect dynamics of massive particles. And this was a recent paper by one of our PhD students. He talked about how the free particle dynamics, if you look at it with two different choices of position observable, you can see completely different dynamics depending on what position observable you're considering. If you consider a frame-dependent coordinate separation, then as a free particle, you can see unitary dynamics, whereas if you consider a frame-independent geodesic separation, you would see dissipative dynamics. This part technically was already seen in Parikh-Wilczek's paper, especially the dissipative dynamics part. And this is something which is very well known. So this is fine. But when you consider harmonically bound particles of this kind, which can effectively be treated as a reduced mass in an oscillator and a center of mass motion mode, you would still see that the frame-dependent coordinate separation has a frequency shift in the frequency omega, which is shown here, which goes like the logarithm of the UV cutoff that is introduced to regularize divergence. Whereas in the frame-independent geodesic separation, if you consider that as a position variable, then the frequency shift goes like the cubic, goes like omega max cubed, which is the cutoff frequency cubed. So you can really see how the dynamics itself seems affected by the choice of the position observable. So this was an interesting paper to check how it becomes crucial that one chooses the frame independence. One also considers frame dependence or frame independence into the consideration when we are bringing up position observables. Yeah. The frame dependent part, both the unitary dynamics and the frequency shift is exactly what you would expect if you consider electromagnetic fields. So there's no surprises there. But if you consider frame independent geodesic separation, it becomes different. Okay, summary of my results. So the approach that I'm offering, we are offering, gives you the advantage that if you have the 2-point correlation function of the space-time fluctuation, you will be able to see what interferometric output you should get, considering you also know the geometry of the setup. And this is an approach which can easily evaluate the pros and cons of the different setups and what you can do with which setup. The strengths of each setup is assessed better this way. And we are also, our ongoing work is to assess and improve the efficiency of stochastic phase difference with optical interferometry, using more robust techniques like parameter estimation. And also we want to work on more generalizations like non-stationarity and things like that. So yeah, that's also part of our work. And ongoing work from our group also includes understanding the fundamental nature of gravity using probes even other than the interferometers. Thank you.
Thank you very much for that. Yes.
I have a question about just trying to understand how the signal appears in the detector. If you have a correlation length that's smaller than the length of the arm, you have an optical field that's going through that arm plus quite that's then kind of is there some phase diffusion in happening like you said, but I guess what I don't understand is if the correlation length is small, how is there not just an averaging out of the final phase seen in the interference pattern?
There is an averaging out. That's why you see the average strength gamma S which is coming out, or the correlation length LR which is coming out. The actual fluctuation could happen at a length scale which is different, or a strength which is different from the gamma S that is mentioned. The W need not be exactly gamma S itself. Is this answering your question, or am I not?
Yeah, so I guess at the end, the variance of that phase in a sense, of that interference pattern is more what you'd be detecting, I guess.
Yes.
I see. And then, well, speaking of this PSD actually of the signal, I understood what you're talking about the comparing the different experiments. What about, but I didn't, unless I missed it, you weren't comparing them yet to, say, the noise budget at LIGO, for example, to actually compare that signal, to see if you had a signal to noise bigger than one.
Ah, okay.
Overall amplitude maybe to that spectrum of fluctuations.
Okay, I didn't mention the numerical values of numerical bounds that can be set up by actual experiments, because it's also a part of the ongoing work which we are trying to do, by which we are trying to constrain the different gravity models that we have here using the actual experimental data from LIGO or from other experimental setups. One reason is that LIGO measures at a frequency range, which I showed you, 0.04 nu to 0.4 nu. They do measure high frequency ranges, but that data is not yet released. So for example, their sensitivity at 100 Hertz, which is very much at the low frequency range for us, is 10 power minus 22 meters. But their high frequency sensitivity, we have no idea of. They have not yet released the data. They have measured it. Sander, who's a collaborator of mine, is actually in the LIGO collaboration. He has access to the data, but because it is unpublished data, he can't give it to us. So he says that once it becomes published, then we can definitely go forward with the paper. So answer to your question, I still don't know how to do the comparison yet.
Most likely it's short noise. Anyway.
Yeah, you would expect it to be short noise, but the thing is that most of these interferometers are made sensitive in a particular frequency range. Beyond that, they always have other noises from either the electronics, or it can be acoustic noises, it can be different things. They are optimized to a range. And anything beyond that range, you cannot really say what is happening. It needs to be measured to figure out. And as how do we actually constrain it? We look at the noise floor of these setups and assume all the noise which is coming at the noise floor is coming because of spacetime fluctuations. So we are actually giving an upper bound to the spacetime fluctuations as of now. We are also, that's why we are trying to use parameter estimation techniques, because we want to see if it is possible to estimate directly instead of just bounding parameters.
So I have a question from the online audience. That is any of the experimental setups sensitive to the polarization of the gravitons?
No, not really. Not the interferometers, I guess.
Okay. Is there any other setup that look at their polarization?
I'm not aware. I'm sorry.
You would think that the correlation, like in terms of deciding between different models, you would think that the Lorenz invariance essentially doesn't give you much choice, and that maybe there's one or two classes. Do you notice that, or is it a bit of a zoo?
For example, some of the features are very common. We notice that the inverse decay is more common, for instance. That is coming because if you consider any field theoretic model or a scalar field based fluctuation, then you're inevitably going to the 1/r type decay. So that was a very common feature. That's why we considered inverse decay specifically. Other than that, some of the features which are common again include non-local correlations, which most gravity models also seem to be considering. That's why we put the step function there. Yeah, other than that, I don't remember. Specifically to Lorentz invariance,
You would think in momentum space you can go like 1 over p squared, 1 over p to the 4th, and that's pretty much.
yeah. Mm. I don't see specific manifestations of that. Maybe I've not noticed. I have to, yeah. Yes, yes, thank you.
Should we?
Also, Dr. do you want to go ahead? Yeah, so what I was more interested in is you're saying you're also comparing the class of models where vacuum, the quantum vacuum gravity uses fluctuations.
Yeah, yeah.
Are those, I mean, is it expected for them to, there must be some computations of how much the magnitude is, right?
Yes.
Is that anywhere near to what one can detect? And other things that they feel space, they exponentially follow, because it's like vacuum intentionally, exponentially small with the distance, right? And you're measuring the correlation between the distance, right? So-
Okay, LIGO is really a long distance. We don't expect to see any cross correlation between the two LIGO setups.
Right.
But the other setups like Quest and GQuest, the setups are separated by a meter and can be reduced to some extent.
Right. So vacuum kind of correlations across that distance is there. People expect that. to be
Yes,
there.
with certain models, holographic models which talk about long range correlations, you can see some correlation.
Right.
But if you're talking about effective quantum field theories,
Right.
neither the strength nor the
Right.
ranges are really conducive for detection, because you're then talking about Planck length scale
Right.
fluctuations. Then
Right. And quick question regarding the space-time exponential decay. That sounds very weird to me because if you're outside light cone, space light, of course, exponential decay. When you're inside a light cone, right, it's dynamics happening in the system. So there's no need for exponential decay during dynamics.
Yeah,
Right? It's
I
like-
don't. That was done for symmetry
Okay.
of models,
Okay.
basically. We saw models only till you're talking about.
Yeah, the space-time exponential.
This C2.
Yeah.
We saw models only till C1. C2 is a generalization that I introduced because we were doing B1, B2. I
I see.
thought, let me also do C1, C2 for completion.
Okay, okay. Thank you.
So I think the question is related to what Sugata was asking. Like, people can hear, is this on? Okay. I was just mostly wondering about well, I didn't see Einstein's equations anywhere, and
Okay.
I mean, or in particular, well, if you were using the linearized type Einstein equations, then you would get the Planck-like correlations that you're saying you can't measure. So I mean, undoubtedly, this would give some big deviations from Einstein's equations.
No, okay, Einstein's equations would be necessary if you're considering massive bodies which are interacting, right? I mean, this is relativistic wave equation that we've used, which is light, which is being modified when.
No, I'm saying the rho satisfying Einstein's equation with the perturbative.
Okay.
Einstein.
The rows, we just took it off from different people's papers. So
But I was just trying to understand that, how much, undoubtedly the rho satisfies some equation. So how different from Einstein's equations is that equation?
Okay, for one specific source that I can immediately quote that comes into my head is the inverse correlation class. The spatial separation that stems from a scalar field model of spacetime fluctuation directly, because both Daniel Carney's paper and the Deely et al. Paper, which is the geotropic fluctuations paper by Catherine Zurek's group. Both those models talk about a scalar field, which is fluctuating. Zurek named it Pixelon. So it's a Pixelon model where you have the scalar field, which is going at light speed or 1/√3 of light speed, which models the space-time fluctuation for. That is coming from just the field equation, wave equation, plane wave equation.
I think Dan showed that those models do violate the semi-classical.
Okay.
They do violate Einstein's image. They don't.
Yeah,
Things with-
I think so. Yeah, I won't exactly remember.
We have a coffee break soon, but unless there are any more questions. Let's leave it there. Thank you very much.
Sorry about overshooting time.